So, welcome back. We can start the first session of the second day, third session of the second day, and first session of the afternoon. So, welcome back from the nice lunch. I think we are starting getting spoiled here, too much probably. So, welcome back also to the online audience. This afternoon we have a rich program, and the first session of this afternoon comprises 4 talks. The first one is entitled Streamwise Periodic Flow Solver with Isothermal Boundaries in SU2, and is given by Dr. Carlo de Servi, who is also a close colleague of mine. He's a researcher and assistant professor in our group in Delft, as well as a senior researcher at Flemish Institute of Technical Research in Belgium. And on behalf of VITO, today is giving this interesting talk. Carlo, the floor is yours.
Thanks, Matteo, for your presentation. I'm now curious to know what do you eat at lunch, but I will ask you that later. Good afternoon to everybody, and today I'm going to present you some recent work we carry out at VITO, the Flemish Institute for Technical Research in Belgium, about the Streamwise Periodic Flow Solver in SU2. In particular, we are busy extending the current implementation of the method to treat also heat transfer problems where the heat transfer surface can be assumed at constant temperature. Let me first give you some background information. Why we are interested in the periodic flow solver. This work initiated by our research at VITO on advanced simulation and design methods for compact heat exchangers. Compact heat exchangers are complicated heat transfer devices that feature multiple flow channels in parallel, a complicated flow arrangement, and where the heat transfer area is generally extended through fins or complicated channel shapes. It results that the safety simulation of a whole compact heat exchanger is out of discussion with the computational resources nowadays available, even with a supercomputer. Especially if on top of the safety simulation you want to also to perform optimization. Then we need a reduced order modeling technique, and better if this technique is physically based, like it is the case of the Streamwise periodic flow solver. Indeed, this modeling method is based on the observation that if you have a channel with a periodic structure, also the flow within the channel will exhibit some periodic patterns. In particular, if we decompose the channel geometry, the periodic channel geometry, into the so-called unit cell, that is an elementary element of this periodic geometry, we can observe that the velocity at the same relative position in the unit cell tends to be the same. Similar consideration can be made also for other thermodynamic quantities of interest for a transfer problem like pressure and temperature. In particular, for these quantities, we can observe a trend that's essentially 2 patterns: a constant variation along the channel, over which we can superimpose a periodic fluctuation, like it is qualitatively sketched in the for the pressure in the chart in the slide. Now, we can exploit this characteristic of the flow to reduce drastically the computational domain to the entire channel to a single unit cell of the channel. This is what the periodic flow solver does. Of course, this is we lose some information when we do so much the computational domain. It's mainly in relation to the so-called entrance effects, so the effects that derive the flow at the beginning of the channel. But apart from these, since the entrance effects are generally limited in a small portion of the channel, the approximation can be accepted, and the reduction in computational cost is large. Now, as I told you at the beginning of the presentation, there is already a periodic flow solver implemented in SU2, and this work has been done by Tobias Katman in the recent years. In the slides are reported some a solution of the performed with the periodic flow solver for the flow around pin thin. The solution of the flow field has been computed with the periodic flow solver in SU2 and the open form. As you can see, the results are identical. So there is in SU2 Streamwise periodic flow solver that is working perfectly. But what about the temperature field? Or equivalently, the energy equation? Here there is the problem. So the periodic flow solver does consider only one side of the channel. This implies that we had to model what happens to on the other side of our channel by setting an appropriate thermal boundary condition. The current implementation of SU2 is valid for constant heat flux boundary condition. So at the wall, we had to prescribe a predefined value of the heat flux. This boundary condition is representative of heat transfer devices like heat sinks or thermally balanced heat exchangers, namely heat exchangers where the two streams have practically the same heat capacity rate, and then the temperature difference between the two fluids tends to be to remain constant along the heat exchanger channel. Unfortunately, these heat transfer devices are only a very tiny fraction of all the heat transfer devices we can find used in industry. Thus, it's interesting to try to include in the current implementation of the periodic flow solver in SU2 additional boundary condition. In particular, one.
Carlo, you're breaking.
Do you hear me now? Sorry.
It's on our. Yeah, now yes.
Yeah, the only thing is that the slide I don't go ahead, so it seems stuck the presentation.
Try to go ahead.
No. There was some delay before. It's not possible that it's my connection because I'm connected to the glass fiber.
Hey, Carlo, sorry, I think that was on our side. Can you hear us okay now?
Yes, yes.
If it's okay with you, can you please turn your webcam off just to lower bandwidth a little bit? Yeah, I think it's on our side, but
yeah.
The only problem is going ahead with the presentation because the slide seems to be
okay.
stuck.
Let me double check that you have control.
Take the chair.
Oh, you're fine.
Otherwise, Matteo, I can tell you when.
Okay, can you try again? Can you try again? Hello?
No, it doesn't work.
Still no. Okay. It says you have control. Okay, if not, we can just flip it for you, if it's okay. Matteo, if you just tell us when to flip.
You'll have 2 minutes extra.
Thanks, Matteo.
Tell me where you are, or here?
Yes, I was on the slide 6.
Where you have the 2 heat exchangers.
Where I have the 2 heat exchangers. Yes, I was discussing the constant heat flux wall boundary condition, the applications that can be modeled with that, and then, but maybe. So you're changing the slide, but
1 more minute, Carlo. Sorry about that.
Because what I can do is to go out and rejoin.
Hold on, Carlo. Give us just 1 moment. We're having a little bit of technical difficulty here.
Apologies for the unexpected hiccup. You have, of course, more time.
Thank you, Matteo. Yes, as I was mentioning before this interruption, the current implementation of the periodic flow solver in SU2 does consider only constant flux as thermal boundary condition. In this work, we dealt with the implementation in SU2 of the constant wall temperature boundary condition, and this boundary condition can be used to model other kind of heat transfer devices like condensers and evaporators. Now, the first step of this work consisted in deriving the corresponding energy equation. I will show you now only qualitatively, given the limited time, how the derivation of the energy equation was performed. First of all, we have to isolate, we have to rescale the temperature field appropriately to isolate the periodic fluctuation of the temperature within the unit cell. And a suitable method to do this was proposed by Patankar in the late 70s, and is based on the observation that we have a flow through a channel with constant temperature at the walls. The temperature variation will be qualitatively like the one depicted in the chart, the left-hand side of the slide. We can recognize there an exponential variation, a variation of the temperature that follows an exponential trend. And on top of this exponential variation, we can recognize a periodic fluctuation. The idea proposed by Patankar was to rescale the temperature field with respect to the mean temperature that follows the exponential variation along the channel length. In this way, we can isolate only the periodic fluctuation. In mathematical form, this corresponds to the second equation in the slide, where the derivative of the difference between these mean temperature or reference temperature with respect to the wall temperature is defined as lambda L, and this is practically equivalent to define the variation of the reference temperature according to an exponential trend. Now, in the original formulation of Patankar, lambda L does not have a constant value for the unit cell. Actually, its value varies depending on the position in the unit cell. This is because the cross-section of the flow changes. The fact that lambda L is not a constant introduces some complexity in numerical scheme and unnecessary approximation in the periodic flow solver. Now, in more recently, Bookings in his PhD work demonstrated that if the reference temperature is taken equal to the double volume average of the temperature over the unit cell, then lambda L is constant. Now, for you is more or less an act of fate at this stage, but I refer you to the PhD thesis of Bookings for the demonstration. And the fact that lambda L is constant allows to simplify considerably the numerical scheme and the energy equation that we want to implement for the constant temperature, constant wall temperature boundary condition. In particular, if we replace in the energy equation the definition of theta according to Patankar and that of lambda L according to Bookings, we obtain the energy equation reported in the slide, where we can see on the right-hand side of the energy equation a source term that consists of essentially two contributions. Formulation depends on the flow regime. In particular, the terms highlighted in purple were already derived by other authors in the literature and are valid for the laminar regime. The terms instead in the bluish box are those that have to be added to the energy equation when we are in the turbulent regime. To the best of our knowledge, there is no other source in the literature reporting how these source term on the right-hand side of the energy equation has to be formulated for the turbulent regime. This represents then a sort of original contribution of this work in addition to the implementation we have performed in SU2. Now, how we compute lambda L, of course. Lambda L can be calculated solving a quadratic equation. In particular, lambda L is the negative solution of this quadratic equation, and the terms of this quadratic equation depends on the value of theta over the unit cell. This implies that the solution of the energy equation requires an iterative scheme, where we solve the energy equation assuming given value of lambda. Once the theta field is the solution of the theta field is converged, we calculate the terms of the quadratic equation to calculate lambda L. And with the new value of lambda L, we recalculate the temperature field, the theta field, the reduced scale temperature, the reduced temperature field till convergence is achieved. To ensure the convergence of the numerical scheme, a stronger relaxation factor is needed for the value of lambda L. This is equivalent to solve a sort of eigenvalue problem of the energy equation. Now, the implementation for both the laminar regime and the turbulent regime has been carried out in SU2. I will show you some preliminary results obtained for a flow around a pin fin. These simulations were essentially targeted to validate, verify our implementation. In particular, for the laminar regime, we could compare our results with data in the literature. In the slide, you see the temperature, velocity, and pressure profile at different position along the unit cell compared with the results in the literature, and we can see that the implementation is correct. For the turbulent regime, we were not able to find data in the literature, so the idea here is to generate a solution that can be compared with the solution of the Streamwise periodic flow solver by running run simulations with an array of multiple pin fins to achieve periodic flow. And this work is still ongoing, so I cannot show it those results today. But in any case, the turbulent regime, the periodic flow solver for the turbulent regime is already working, and I reported here in the slide.
2 minutes, please. You can. Thank you.
Sorry, Matteo, I had to stop for 2 minutes.
No, you have to go. You still have 2 minutes.
Okay, so sorry. No, yes, I reported here in the slide a validation of the joint gradients calculated for the deformation of the pin fin. And as you can see, the match with the joint gradients with finite difference calculated through the parameterization tool Parablade is very good. So we can say that the implementation has been successfully achieved. And I can conclude then my presentation saying that for the laminar flow regime, we already performed a verification of the solution, and everything is according to the theory. For the turbulent regime, we are in the process of generating a reference solution with Orange code, but in the future, we may consider also to use higher fidelity flow solvers like LES solver to indeed provide more insight on the validity of the Streamwise periodic flow solver for the turbulent regime. And once these verification validation studies will be concluded, the idea is to use the optimization framework with SU2 to study the optimal shape of the fins as a function of the dimensionless numbers that govern the heat transfer, the prime number of the fluid and the Reynolds number. And with this, I have concluded my presentation, and I thank you for your attending this presentation, and I'm available here now for answering your questions.
Thank you, Carlo, for the great talk. Let's shake a bit the audience. Is there any question? I have one question for you, Carlo, then I expect one from some of you. So about the teaser, has the teaser been, run with SU2 or something different?
Open form.
Okay. Would be interesting to see how SU2 works for that test case. Then there is a question from Toby.
Yeah, thanks for the words. I have one question with really to use let's say the non-Streamwise periodic approach with an outlet competency and to mess with all the boundary conditions that are applied on the surface. But I would be interested in seeing comparison of this new hypersonic necessary approach against this kind of non-physical outlet approach. I'm not sure if you.
Matteo, there is a lot of echo, so if you can.
I'm going to repeat the question if I got it. So Toby is asking whether you compare the results of your Streamwise turbulent periodic flow solver with those of a non-Streamwise solver.
Not yet. Of course, it depends which solver we are using. If we are using RANS code, then we simulate multiple pin fins, an array with multiple pin fins. We already noticed that a certain distance from the entrance of the channel, we get a periodic flow, and there is a perfect match for the flow field and the temperature field in the case of a laminar regime with the calculation of the Streamwise periodic flow solver. Of course, there is an equivalency between the Streamwise periodic flow solver and the RANS solver once the flow is fully developed. I don't know if this equivalency exists if we use, for example, an LES solver. Because that case we can have different contributions due to the turbulence that are not counted in Streamwise periodic flow solver, because basically the turbulence in the Streamwise periodic flow solver is equivalent to that of a RANS code.
Okay, are you satisfied? Good.